1.
Hi students, today we are talking about radian measure and angles on the Cartesian plane. So our learning goals today are we're going to create the special triangles, which you may or may not remember. Sorry about that. But instead of degrees, we're going to be using radians, okay? So we're going to change everything over to radians. Then we're going to go over the definitions of sine, cos, and tan and their reciprocals using x, y, and r in the unit circle on the Cartesian plane. Look at the cast rule and then use all that to solve for unknown trig ratios and unknown angles. So recall that we can use special triangles to come up with exact values of trig ratios in these two special triangles. So our first special triangle is a right triangle. Okay, so what's special about that is that we have 45 degrees here and 45 degrees here and of course 90 degrees here. Okay, so we want to make the side lengths as simple to work with as possible. This is because sine, cos, and tan are just ratios. So if we made the side length 2, this side length would also have to be 2. It's an isosceles right triangle. Okay, if this side was 5, this side would be 5 as well. So really we could use anything that we wanted, but we're using the simplest length. So we're going to make this side 1 and this side 1. Because of a Pythagorean theorem, that means the hypotenuse would be √2 long. So then the sine of 45 degrees is 1 over √2, SOHCAHTOA, right? Opposite over hypotenuse. The cos of 45 degrees, adjacent over hypotenuse, 1 over √2. And the tan, TOA, opposite over adjacent, is 1 over 1. Okay, the other special triangle is half of an equilateral. So we don't actually use the whole equilateral, we just use this half of it. So this would be 60 degrees because in equilateral, they all have to add to 180, but they'd be even. So all of these would be 60 degrees. And since this has been cut in half, this would be 30 degrees here. Now, in this case, we say that each side length is worth 2 in the equilateral, so that when we cut it in half, this is worth 1. If we made each side length 1, then we would have a fraction here, which we don't like. Okay, and then using Pythagorean theorem, we can deduce that the height there would be √3. So again, you can use this triangle together with SOHCAHTOA to come up with the exact value of the cos, sine, and tan of 60 degrees and 30 degrees. So for example, the sine of 60 degrees, sine is opposite over hypotenuse, will be √3 divided by 2. If you put it into your calculator, sine of 60, see what you get. You get a decimal. So a decimal is always an estimation, whereas √3 over 2 is an exact number. And as mathematicians, we like to be exact. Okay, so now we're going to switch over everything to radians instead, so we can get used to that. So instead of pi over 2, instead of 45 degrees, we get pi over 4. Recall that pi is just the same as 180 degrees, and 45 degrees is just a quarter of 180, so it makes sense that that is pi over 4. You can also use the formula to convert if needed. Okay, so then this is also pi over 4. And this is 1 and 1 and √2. All right, so here's that, the right angle. Then instead of 60 degrees, we have pi over 3. Okay, and then this is pi over 6. Okay, this is still 2, 1, and √3. All right, so now these are the new special triangles you guys need to memorize because everything in grade 12 will be in radians, not degrees any longer. So therefore, this chart is now filled out, but everything is in terms of radians instead of in terms of degrees. So the sine, cos, and tan, and the reciprocals, cosecant, secant, and cotangent can all be found using these two special triangles. So you guys can see it would be a lot of work to memorize all of these different ratios. What's better is to memorize the two special triangles and recall how to find sine, cos, and tan and their reciprocals using SOHCAHTOA. Okay, let's also recall that angles can be expressed on a Cartesian plane. As a terminal arm is swung about the origin, a circle is created. So if this was the terminal arm, you could swing it around and it would make a circle, right? This, however long the radius is, would make a circle with radius r all the way around. So we could define the trig ratios in terms of x, y, and r. So let's drop down and make a right triangle because we need right triangles to talk about trig, okay? So let's say this is theta. Okay, so if this is theta, then the length here is defined by the x value. The distance here, the height here, is defined by the y value. And then this length here is the radius of the circle. So remember, sine, SOHCAHTOA, sine is opposite over hypotenuse. So opposite is y, and the hypotenuse is r. Okay, cos is adjacent over hypotenuse, so x over r. Sorry, they should say sine of theta, cos of theta. And then tan of theta, tan TOA, opposite over adjacent, is y over x. Okay, now the reciprocal of sine is cosecant of theta is equal to r over y. Then you just flip top and bottom. Sec theta or secant theta is r over x, and cotangent theta or cot theta is x over y. All right, so that is how you find it if it's in the first quadrant. But what if we move around and we have angles that are larger than pi over 2? So what if we have an angle here that's between pi and 3 pi over 2? So we'll call that theta. So the trig ratios for any principal angle, theta, can be found by determining the related acute angle. Do you guys remember this? The related acute angle. And remember, we label that guy with beta, so like a fancy B here. So beta is always formed between the terminal arm, so that's this guy, and the x-axis, okay? So it never touches the y-axis, it always touches the x-axis. So then you can create a right triangle with beta and the x-axis. So this is y, and this is x, and this remains r. So just remember that sine of theta, so sine of, actually I should do that in a different color. Recall that sine of theta, so your big angle, is equal to, that the absolute value of the sine of theta is equal to the absolute value of the sine of beta. Okay, so their values are the exact same. What might change is which one is positive and which one is negative. Okay, cos of theta, its absolute value, okay, so the actual number is equal to the cos of beta. But again, the absolute value, so just the number part. Okay, you can't, we have to use the cast rule to look at what's positive and what's negative. And then the absolute value of the tan of theta, so the big angle, the principal angle, is equal to the tan of whatever that related acute angle is, or at least the value. Okay, again, positive and negative might change. Okay, so the sine, cos, and tan of the related acute angle are the same value as the sine, cos, and tan of the big angle, theta. It's just the positive or the negative that might change. So the cast rule defines in which quadrant where each ratio is positive. So we start down here and go C, A, S, T. So that means that all ratios are positive in this quadrant. Only sine is positive in this quadrant. Only tan is positive in this quadrant. And only cos is positive in this quadrant. Okay, now the cast rule is all well and good, but I want to explain why the cast rule is what it is. And again, we talked about this last year. So remember that sine is just y over r, okay? And the radius is always positive. So wherever y is positive, sine will also be positive. Okay, and wherever y is negative, sine will also be negative. So it makes sense that in this quadrant, these two quadrants, sine is positive in both of them, because in both of those quadrants, y is positive. And down here, sine is negative, because that's where y is negative. Okay, cosecant, remember, is just x over r. So wherever x is positive, cos is positive. And wherever x is negative, cos is negative. Okay, so again, cos is positive in these two quadrants. That's where x is positive, and negative in these two quadrants where x is negative. Finally, tan is y over x, which could be looked at as the same as slope. So wherever the slope of a line or the angle is positive, tan will be positive. And wherever slope is negative, tan will be negative. So slope is positive in this quadrant and this quadrant, right? A line this way or this way, that would be a positive slope. So tan's positive there. And in either one of these quadrants, the line would be sloping negatively. So tan is negative there. Isn't that just so exciting? All right, let's get to the meat and potatoes here, some actual examples. So determine the exact value of the sine of pi over 2. So pi over 2 is the same as 90 degrees. So you guys might still need to be doing some conversion in your head to remember where these things go. But remember, pi is here. Always just label that. And so that helps you realize, oh, pi over 2 is here. So that means this is your angle theta. So if the sine of pi over 2, remember, is y over r. So whatever the y value is here is going to be equal to whatever the radius is. So you're going to get a 1-to-1 ratio. So therefore you get 1. Or you can just say, like, let the radius of this circle be 1. So therefore y must be 1. So then sine of pi over 2 is 1 over 1, which is 1. Now say you would let the radius be 10. Well, then y would also be 10. And 10 divided by 10 is 1. Say you'd let the radius be 5.2. Then the y value there would have also been 5.2. So again, you get a 1-to-1 ratio, so the value there is positive 1. Now what about the cotangent of 3 pi over 2? Well, remember, this is pi, and this is 0 and 2 pi. This is pi over 2, so this here must be 3 pi over 2, right? 1.5 pi's. So, man, I could go for 1.5 pi's. So here's your theta. So if you had a terminal arm there, how would you come up with the cotangent? So cotangent of 3 pi over 2, remind yourself that that's just the inverse of tangent, so it's x over y. Well, the x value here is 0 no matter what y is, so the solution to that is just 0 because you're on the y-axis. Okay, let's get a bit more difficult now. The cosine of 5 pi over 4. So we have to determine what quadrant this is in. So 5 pi over 4, you can also think about this as 5 over 4 pi. So, so that means it's just slightly above pi, but it's less than 1.5 pi. So you're determining in this quadrant. Okay, so now your theta, so this here, your theta is equal to 5 pi over 4. There it is. So you need to come up with the cosine of that. So because it's not in the first quadrant, you need to label your related acute angle. There. Okay, so to find beta, it's just 5 pi over 4 minus pi, because that's what's left. So it's this whole green minus just this pi. So beta is equal to 5 pi over 4. That's the whole angle, minus pi. So then you can get a common denominator. And you'll see that you're just left with 1 pi over 4. So this beta here is just pi over 4. Okay, so now we just need to find the cos of pi over 4, which in this, so we can go back to our special triangle, right? That's from the 90 degree, the isosceles one. I was having a brain for it there. So it's adjacent over hypotenuse, so 1 over root 2. So therefore, that means that the cos of 5 pi over 4 is either 1 over root 2 or it's negative 1 over root 2. So we know for sure that the value is 1 over root 2, but is it positive or negative? Well, then you look at what quadrant it's in. It's in this quadrant, so you just have to think, is cos positive here or negative? According to the cast rule, cos is only positive here, and then we're all are positive here. So therefore, it's negative there. You could also think cos is related to x, and x is negative in this quadrant, so therefore it's negative. So my answer is negative 1 over root 2. Now, you'll notice in the back of your textbook that they might have it written like this, minus root 2 over 2, and you'll think you got the answer wrong. These numbers are actually the exact same thing, and I'll show you why. There's something called rationalizing the denominator, and that means they don't like having a square root in the denominator, just like having a decimal or a negative sign in the denominator. It's okay to have it in the numerator, but in math, often we don't like it in the denominator. So what we do is we multiply this by root 2. No! Okay, close. There we go. By root 2 over root 2. Why does this work? Well, root 2 over root 2 is just 1, so we're not actually changing the value of this. But notice root 2 times root 2 just gives you 2, so you no longer have a denominator that's a radical. And so then your numerator becomes minus 1 times root 2, so minus root 2. All right, so if your denominator is a radical, you'll often see it rewritten where your denominator is not a radical, and that's how they do it. Okay, it might be a good exercise during class time to go through your table and change everything so that the numerator is not a radical, just so you're not making mistakes or feeling like you got the wrong answer when really you did. When you did get the right answer. Okay, one more example here. So the cosecant of 11 pi over 6. So you have to think, how big is 11 pi over 6? Well, it's slightly smaller than 12 pi over 6, which would be 2 pi. But it's bigger than 1.5 pi, which would be here. So it ends in this quadrant. So here is our angle, 11 pi over 6. So it's not in the first quadrant, so you need to find the related acute angle. So to find beta, you just, again, you do 2 pi. Is that behind my head? Here, let me do it up here. 2 pi minus 11 pi over 6. And you can get a common denominator. You get pi over 6 is what's left. So that means this related acute angle is pi over 6. So to find the cosecant here, we need to find the cosecant of pi over 6. Okay, so again, cosecant of pi over 6, that's from this triangle, so I'd just like to draw it. So pi over 6 is up in this corner, and this is root 3, 3, 2, and 1. Cosecant is the inverse of sine. So sine is opposite over hypotenuse, so this would be hypotenuse over opposite, so 2 over 1, so just 2. So now we got to decide, is the cosecant of 11 pi over 6 2 or negative 2? Well, sine is negative in this quadrant because y is negative, so therefore the cosecant will also be negative, so that answer is negative 2. So here I go through the basic steps of how to solve these questions. First, you need to determine where the quadrant where theta lies, okay, using your knowledge of where pi, pi over 2, 3 pi over 2, and 2 pi are. So just to remind yourself, this would be 0, pi over 2, pi, and 3 pi over 2, and then it circles around to 2 pi. So you have to figure out which of these 4 quadrants does your angle terminate in when you're given the angle in radians. Then you need to identify the related acute angle. You label the right triangle, and you solve for the trig ratio, and then you apply the cast rule. So you solve for the trig ratio of beta, and then you apply the cast rule to say, is theta plus or minus? whatever it was for beta. Okay, there's one more example in this note, and it goes the opposite way. So in this example, you're going to be given the tangent, and you actually have to go back and solve for theta. So this involves quite a bit more analysis. And I'll be honest, I'm making this video right before 5th period and the bell's about to ring. So I'm going to do this example on a separate video. So thanks for watching. So there's the bell. Thanks for watching. Hope you learned lots.